Thank you. I'd like to thank the organizers for the invitation to speak here and also for organizing such an interesting conference. I'm going to be talking about results in a paper that appeared on the archive a month or two ago, work done in collaboration with a graduate student, Yuxiao Wu, at the University of Chicago. So I'm going to start with a very brief introduction and sort of summary of what I'm going to be saying. And I'm then going to present some data, which is a very explicit example of a general relation that I'm going to be talking about. And after having presented that data, I'm going to present kind of a theory of how to explain the data. And it's going to be in the context of rational conformal field theory, and it involves generalizing Hecke operators, which are familiar to many mathematicians that work in the area of number theory, and also has appeared in conformal field theory. But the Hecke operators that we'll be describing are a bit of a variant of the standard ones. So I'll talk about the standard Hecke operators, talk about how they can be generalized to apply to characters of rational conformal field theories, and then give some applications and examples, and then end with some questions and speculations about what they might be good for. So I'm going to be talking about a new relationship between characters of rational conformal field theories. It generalizes previous relations that go under the name of Galois symmetry that might be familiar to some of you that have worked on rational conformal field theory, otherwise they may not. Those are relationships between the representations of the modular group provided by characters of rational conformal field theories, and what we'll be doing is embedding that into a larger theory which relates not only the modular representation, but the actual characters themselves. So I'll discuss these new relations, explain how they tie together a number of scattered results in the literature, and then talk about some applications. So in order to introduce the data, I have to just give a couple of definitions. So I'm going to talk about two examples of two-dimensional conformal field theories. They might seem kind of random, but they were not picked randomly. So the first is the Yang-Lee model. This is a non-unitary minimal model. It has two independent characters. Because it's non-unitary, it's a little confusing which you should call the vacuum character, but anyway, I've labeled them in a particular way. These characters are well known in the mathematical literature. They are functions that satisfy the Rogers-Ramanujan identities, but that won't be needed for right now. And then there's another unitary rational conformal field theory, affine G2 at level 1, which also has two independent characters. And I've expanded those as an expansion in Q. So I basically am going to explain a relationship between a bunch of coefficients here that are the coefficients in the Q expansion of the independent characters of two different rational conformal field theories. So here's some data, and it's a little confusing, and there's some funny numbers here, but bear with me. So this table are the coefficients of what I call C1/5 for the Yang-Lee model. So this is the coefficient C of 1, C of 2, 3, 4, 5, 6, 7, then C of 8, C of 9, C of 10, and so on. So I've arranged them so that the columns are the coefficient C of n, where n is equal to a particular number mod 7. In particular, this column here are all the coefficients C of n, where n is equal to 6 mod 7. So these were the coefficients of the character of one of the characters of the Yang-Lee model. Here are the coefficients in affine G2 at level 1 divided by 7. And you'll see that the coefficients in this column are almost exactly the same as the coefficients in this column. So 120, 120, 261, 261, but then 551, 3858 over 7, those two numbers differ by a seventh. So every seventh term, it turns out there's a little discrepancy. So this is the data. Why should these numbers be so clearly related? What's the explanation for this discrepancy? someone who knows a bit about Hecke operators might recognize this, but it looks a little strange anyway. I'll try to explain exactly where this relationship comes from. So the framework is that of rational conformal field theory, and so I want to just remind you of the basics. So in a rational conformal field theory, we have some representation of a chiral algebra. For minimal models, which I'll often be discussing, that chiral algebra is just Virasoro. For affine Lie algebras, it's Virasoro plus the affine Kac-Moody symmetry. There are other things like the monster module where it's some larger chiral algebra. There are characters, which is the trace in a representation of q to the L naught minus c over 24, c being the usual central charge, q is e to the 2 pi I tau, where tau lives in the upper half plane. And there's a partition function, which is a finite sum of holomorphic and anti-holomorphic characters, and one of the requirements of rational conformal field theory is that that partition function should be modular invariant. So examples include the Ising model, the Yang-Lie model, affine Lie algebras, more exotic things like the monster VOA, the baby monster VOA, which will appear briefly later on, and of course many other examples are known as well. So one of the central things in this talk is going to be the modular properties of the characters of rational conformal field theories. And the characters are weakly holomorphic weight zero vector valued modular functions. So what that means is that there is a representation of a modular group SL2Z, finite dimensional, little n, and we can specify the representation by specifying its value on the generators of the modular group, S, which takes tau to minus 1 over tau, and T, which takes tau to tau plus 1. So the representation of S squared and the representation of S times T cubed have to be an involution because of the group theoretical properties. That involution is usually called the conjugation operator in rational conformal field theory. Now, in a rational conformal field theory, the eigenvalues of the representation of the T matrix are rational numbers. And so there is some integer capital N such that the nth power of the representation of T is the identity. So that capital N is going to play an important role in what follows. And there's a theorem due to Bante that says that gamma of N, the principal congruent subgroup, which is defined to be the elements of SL2Z, where this matrix is congruent to the identity matrix mod capital N, that congruent subgroup is contained in the kernel of rho. So from a practical point of view, what that means is that if you do a modular transformation on the characters of a rational conformal field theory, if the representation is in gamma of n, then it just leaves the character invariant. So each of the components of the character, each of the characters is a modular form for gamma of n, but under transformations in SL2Z mod gamma n, the characters will mix according to the representation rho. Now, perhaps everybody's favorite example of a rational conformal field theory is the Ising model. It has 3 independent characters, a vacuum character, 2 characters corresponding to primary fields of dimension 1/2 and 1/16. And under transformations by S, the characters of minus 1 over tau are rho of S times those of the tau, where rho of S is this 3×3 matrix. And one, in a rational conformal field theory, can always choose the representation of T to be diagonal, and the diagonal entries are just determined by the central charge and the conformal weights of the primary fields. So in this theory, the order of rho of T is 48. And for reasons I'll explain in the next slide or two, I'm also going to call that capital N, that's the order of rho of T, the conductor of the rational conformal field theory. So one other important ingredient is that there's a fusion algebra determined by the Verlinde formula. So given a representation rho of S, one can look at the fusion of primary operators. The tensor product contains the primary operator phi k with some multiplicity nijk, And these multiplicities are famously non-negative integers, which are determined by the representation of rho of S given by the Verlinde formula. So the first thing I want to explain is that the representations rho of the modular group, and therefore the fusion matrices Nij, for some theories are related by Galois symmetry. And I want to explain this because I'm going to be generalizing this relationship of Galois symmetry. So let K be the field that you get by adjoining the matrix elements of the representation rho of the modular group to the rationals. There's a result due to de Boer and Goree that this field K is a finite abelian extension of the rationals. And there's a famous theorem of Kronecker and Weber that says that as a result, K is always contained in some cyclotomic extension of the rationals. So an extension of the rationals by some primitive nth root or mth root of unity. The minimal M, such that K is contained in this cyclotomic extension, is called the conductor of K. And this conductor, for this construction applied to rational conformal field theory, is going to be the same as this capital N, the order of rho of T. Now, this cyclotomic extension has a Galois group that leaves the rationals invariant and moves around the nth roots of unity, and that is isomorphic to the group of units in Z mod NZ. Now, in physics, we often think of Z mod NZ as being a group, which it is, but it's also a ring. So in addition to, say, adding integers mod n, we can also multiply them, but not all elements have a multiplicative inverse. So Z mod, the group of units, is the elements in Z mod NZ that have multiplicative inverses. I'll give you an example on the next slide, but for right now, what I want to say is that for each element L in the group of units, there's a paper by Costa and Gannon that showed that there is an action on the representation of the modular group, where you take the representation of rho of T, and you take it to the nth power, if L is in the group of units, and the action on rho of S is to permute the rows or columns of rho of S and multiply by some signs. And this action we will denote by G sub L. So in order to explain this in a little bit more detail, and at the risk of embarrassing myself to the mathematicians in the audience, I want to explain the group of units in an example. And in talking to non-physicists or non-mathematicians, we often say that Z mod NZ is like doing clock arithmetic. So here's a clock, and I'm going to explain the group of units in the group Z mod 12Z, or in the ring Z mod 12Z. It might be more natural to put 0 up here, but usually clocks have a 12 there rather than a 0, so you'll excuse me. Now, Z mod 12Z, if we think of just doing adding numbers mod 12, just corresponds, it's generated by adding 1. And if I add 1 to 12, I get 13, which is 1 mod 12. So I just do mod 12 arithmetic and look at iterating that transformation. If I now want to look at the group of units, you can easily convince yourself, are the numbers that are relatively prime to 12. For example, 2 has no multiplicative inverse in Z mod 12Z because 2 times any integer is even, and that's never equal to 1 mod 12. Whereas 5 squared is 25, which is equal to 1 mod 12. So that's the group of units. And if I take 5 and I multiply by 5, 1 goes to 5, 5 goes to 1, 11 times 5 is 55, which is 7 mod 12. So it does that. Similarly, multiplying by 7 exchanges the elements of the group of units like that, and multiplying by 11 does that. So this shows you that the group of units is Z2 mod Z2. There's the identity where I do nothing, and I've just exhibited 3 elements of order 2. There are 4 elements in the group, so that uniquely tells you the group is Z2 times Z2. And we can now let it act on the rest of the elements of Z mod 12Z by multiplying by 5 and then reducing mod 12. And so you get this picture of what the group of of units is doing to Z mod 12Z. All right, so how does this appear in rational conformal field theory? Well, we can look at the representation of S in the Yang-Lee model. I've written it in what's not actually a terribly useful way, but you can rewrite 1 over the sine of pi over 5 and sine of 2 pi over 5 in terms of rational numbers in the square root of 5, and the square root of 5 can be expressed as a sum of 5th roots of unity, which is a sum of 60th roots of unity. The conductor for the Yang-Lee model is 60. 7 is relatively prime to 60, so I can act with this element. The F stands for Frobenius. These are often called Frobenius elements. I can write this as an element in Z mod 60Z, take the 7th power, the action of this, and what you find is that you get this matrix times 0 minus 1, 1, 0, and that is the modular representation for affine G2 at level 1. Similarly, I can take the T-mate representation of T and take its 7th power, and that gives me the representation of T in affine G2. And there are similar Galois relations. If you take the Yang-Lee characters and act by 13, you get the modular representation of F4. If you take the modular representation of the Ising model with 3 characters, and this has conductor 48, and you act by the Frobenius element 47, you get the representation of the modular group for the baby monster VOA, which also has 3 independent characters. So these Galois relations are known and have appeared in the literature in a variety of ways. But these are relations between the representations of the modular group provided in a rational conformal field theory. We're going to extend them to a relationship between the actual characters of the rational conformal field theory, and that relationship will then imply these Galois relationships as a consequence. So the relationships involves Hecke operators, and so I want to quickly remind you what Hecke operators are. Modular forms, and now by modular forms I mean ordinary holomorphic modular forms, not the more general modular forms that, for example, Francis Brown was talking about, but just standard functions of tau in the upper half plane, which transform under modular transformations with weight k, can be thought of as 2 ways. This is the usual way that they appear in physics and string theory and conformal field theory, but it's equivalent to thinking of a function of a rank 2 lattice, which under rescaling of the lattice transforms by lambda to the minus k, where lambda is the scale parameter. The relationship between the two is just that if you take 2 complex numbers, omega 1 and omega 2, and you construct the rank 2 lattice that's the integer span of those, that the function of this lattice is just the function of this ratio up to a factor of omega 2. So that's the relationship between the 2 ways of thinking about modular forms. Now, the way when you think in terms of lattices is particularly nice because it allows a very natural definition of what a Hecke operator is. So the Hecke operator simply takes a function of lattices, the Hecke operator is specified by an integer n, and it sums that function over all sublattices of index n in the original lattice. So sublattices of index n, in terms of condensed matter physics, that just means that the fundamental region of the lattice is n times as big. If we look at this lattice here, where omega 1 and omega 2 are the basis vectors, if I want to look at index 6 sublattices, well, I can go over 2 and up 3, which is what I've shown, or I could go up 2 and over 3, or I could go up 6, down 1, and so there are 4 different sublattices of index 6. It's a finite sum, and from the property of f of L, it's clear that acting with this Hecke operator gives you another function of rank 2 lattices, which is, again, a modular form. So Hecke operators take modular forms to modular forms. Now, we'd like to translate that very simple definition in terms of function of lattices back into a function of tau. One way to do that is to notice that you can get any sublattice of index n as an integer combination of basis vectors, a omega 1 plus b omega 2, c omega 1 and d plus d omega 2, where ad minus bc is equal to n in order that it have index n. So we can think of summing over by two matrices of integers with determinant n and looking at the action of those. So that gives us a definition of Hecke operators acting on functions of tau. I now want to look not at elements of SL2Z, but rather 2 by 2 integer matrices that have determinant p. I'm going to choose Hecke operators for prime p just to simplify some formulas. There's a standard action of those on functions of tau. And we sum over the action of those matrices mod the action of SL2Z, which doesn't do anything. So that, again, is a finite sum. You can write an explicit expression for what this coset is. And then you can translate that into an actual relationship between Fourier coefficients. So if you have a modular form, which has a Q expansion in terms of coefficients A of n, then its Hecke image will have some coefficients AP of n, and the formula at the bottom of that slide gives you an explicit expression for the coefficients of the Hecke image in terms of the coefficients of the original modular form. And this depends on the divisibility of n with respect to the prime p. Hecke operators exist for any integer, positive integer, but the formulas are simpler for prime, so I restrict to that. So in math, these are, well, I'm not a mathematician, so I probably shouldn't say, but my understanding is that they are mainly applied to cusp forms, that is, modular forms, which vanish as you go to tau equals I infinity, or more generally to any of the cusps in the fundamental domain, if you are looking at a modular form for some congruent subgroup. A famous example, which occurs in string theory, bosonic string theory, or rather its inverse appears, is the delta, the unique weight 12 cusp form, which is eta to the 24th. And this is a eigenfunction, since it's the unique weight 12 cusp form. It's the eigenfunction of all the Hecke operators, and the eigenvalue of the nth Hecke operator is just the coefficient of q to the n in the q expansion of delta. And, well, they appear all sorts of places in deep aspects of number theory. There are Hecke eigenforms of weight 2 that appear in the modularity theorem. So there's this beautiful mathematical theory where Hecke operators play a very fundamental role. However, the characters of rational conformal field theories cannot be Hecke eigenfunctions. They're certainly not cusp forms, and they're not even really they're not holomorphic modular forms because they blow up as you go to I infinity, because there's always a q to the minus c over 24, or some negative power of q, even in a non-unitary theory. So in rational conformal field theory, if we want to generalize Hecke operators, we have a little bit of a problem because they're not going to be Hecke eigenfunctions, and we also have vector-valued modular forms. There's some finite dimensional representation of the modular group. So we have to solve a few problems if we want to generalize these Hecke operators. But it actually turns out to be quite straightforward to do so. I'm not going to give you the details. You can find them in our paper. But the thing to notice, or to remember, is that the components of the individual characters are modular forms for gamma n, the congruent subgroup. And so it's natural to look at Hecke operators for gamma n. This is a standard mathematical topic which is described in a way that we found useful in a book by Rankin on modular forms in chapter 9. But you also need to use the modular representation properties of rational conformal field theory characters. There's a slight twist to the whole business. And there's a slightly more advanced formalism involving double cosets, which is needed to formulate these Hecke operators, which I'm not going to explain. I'm just going to summarize by telling you how they act on the Q expansions. So on the Fourier coefficients, it's useful to write the characters not in the form that I wrote them earlier, where there's some fractional power of Q and then an integer expansion, but rather to write them as some coefficients bi of n, q to the little n over capital N, where n is the conductor of the rational conformal field theory. These characters are invariant under t to the n, but not under t, so this is the natural Fourier expansion, even though it leads to a lot of zero coefficients. So if you do that, then the Hecke image has coefficients which were related by a formula that's very similar to what I wrote down before. It's diagonal for when p does not divide n, but when p does divide n, there's an additional piece here which involves the representation of the modular group evaluated on a certain matrix, which I have to define for you. So you can prove that with this formula, the Hecke images are again component by component modular forms for gamma n, but they now transform according to a new representation of the modular group. So the representation of the Hecke image on S is that it's rho of sigma ps, and the representation on T is rho of T to the p bar. So I have to tell you what p bar and sigma p are. So p is relatively prime to n. That means that it has a multiplicative inverse. I define p bar to be its multiplicative inverse. Sigma p is the pre-image of this matrix under the mod n map from SL2Z to SL2Z mod nz. So take an element of SL2Z, reduce each element mod n, that's the mod n map, and sigma p is supposed to be an element of SL2Z, which under this mod n map gives you this matrix involving p in its multiplicative inverse. So here's an example. For n equals 60, this is the example that appeared in the Yang-Lee model. For n equals 60 and p equals 7, p bar is 43. 43 times 7. I don't think I can do that while I'm standing in front of an audience, but, well, yeah, I can. Anyway, it's 1 mod 60, as you can work out. And sigma 7 is this matrix, and with a little bit of effort, you can see that this is equal to 43700 mod 60, and if you compute its determinant, it has determinant 1, so it's an element of SL2Z. So you can then show that the change of representation under Hecke is the same as that under this Galois symmetry for L equals to P relatively prime to N. And this equivalence requires certain identities, which are that this Frobenius element acting on the representation of S is rho of sigma P bar S, and acting on rho of T, it's rho of T to the P. So those identities are proved, and so that shows you that the Hecke relation between characters implies a relationship between the modular representations, which is this previously known Galois relation. So let me now discuss some applications. If we go back to the example from the first data slide, you remember that involved coefficients of the Yang-Lee characters and the G2 characters. So my claim is that the characters of affine G2 are the Hecke image under T7 of the characters of the Yang-Lee model. And I wrote that relation in terms of these coefficients I called B, which were the B of n, which were the coefficients of Q to the little n over capital N. But if I translate that back into these coefficients, it boils down to these identities. So remember, C 1/5 of the Yang-Lee model is what I was plotting and comparing it to C naught G2 of n divided by 7. So that gives you this, but then there was this discrepancy, and this is the discrepancy. And because there's this mixing between characters given by this representation of this matrix sigma 7, that discrepancy is determined by the other character of the Yang-Lee model. So if you look at that formula and then compare it to this slide, you'll see that that it explains it exactly. So a few comments on this. This Hecke action preserves the dimension of the representation of the modular group. So if we want to know whether there are other examples or implications of this beyond this Yang-Lee and affine G2 example, we should look at rational conformal field theories that have the same dimension of the modular group. And one way of doing that is to look at modular linear differential equations, because the characters of a rational conformal field theory that has little n independent characters will satisfy an nth order modular linear differential equation. This is an idea that was developed in the physics literature. There's a paper by Anderson and Moore who used it to prove that C and H are rational in rational conformal field theory, work by Iguchi and Oguri, applying this, as I recall, either to minimal models or affine Lie algebras. I don't remember which at the moment. A paper by Mather-Muki and Sen, which I will mention, and then others. And in math, there's an important early paper by Kaneko and Zagier, and many other people have worked on this general approach. I'm going to use it sort of as a tool for describing characters of rational conformal field theories. There are two ways of thinking about it. One is that you have a rational conformal field theory, and you can derive the modular linear differential equation by looking at the existence of null states. The other is you can just postulate the modular linear differential equation, try to classify solutions, and ask whether those solutions are characters of a rational conformal field theory. So these modular linear differential equations start by noting that there's this Ramanujan-Serre derivative, which involves taking d by d tau and then acting on a weight k modular form, the quasi-modular Eisenstein series E2. This changes the weight of a modular form by 2. So if we start acting on something with weight 0, which is true for a character of a rational conformal field theory, and we iterate this, then dn acting on f gives us a weight 2n modular form. So we can then write down a differential equation where every term has weight 2n by multiplying lower powers of this iterated derivative by modular forms of weight 2 times n minus k, where we sum from k equals 0 to n minus 1. And then we have to ask ourselves what properties these coefficient functions should have. So rational conformal field theories do have a pole as you go off to the cusp at I infinity, but you can prove that they converge everywhere else. So they can't have poles anywhere else, but this does not have to be true of the coefficient functions. And to understand the relationship, well, from the standard theory of differential equations, you can express the coefficient functions in terms of a ratio of sort of partial Wronskians over what's often called the modular Wronskian, defined here. So W sub k can't have any poles, but W may have zeros. And what I think in the physics literature is often called the number of zeros of this modular Wronskian is 6 times the sum of the order of W at the Z2 and Z3 orbifold points at the fundamental domain, plus a sum over all interior points, points other than these orbifold points. And then there's a kind of Riemann-Roch type relationship that tells you the order of W at infinity plus this number of zeros over 6 is equal to the weight over 12, and the weight of the modular Wronskian is n times n minus 1. So now you can classify solutions by specifying the order of the modular differential equation and the behavior of the coefficient functions. So the simplest case is second order with no zeros for the modular Wronskian. And then if we write this in terms of ordinary derivatives, d by d tau up to 1 over 2 pi I, then, well, there's this term coming from that script d squared. There are 2 coefficient functions. One of them has to have the modular form of weight 2, but there aren't any, so that's 0. And then another one is a modular form of weight 4, and that's the unique Eisenstein series E4. So there's one coefficient mu, and you can then solve this by the usual, well, Frobenius appears again, the usual Frobenius method, and you find 2 independent solutions depending on mu, and you can try to classify, well, you can classify all values of mu that lead to solutions that are consistent with there being characters of a rational conformal field theory. That means the coefficients in the solution are non-negative integers, and the vacuum appears with degeneracy 1. So if you do that, then Mather, Muki, and Sen showed that you get a finite list of solutions. The first one is the Yang-Lee model, and then you get affine level 1 characters for A1, A2, G2, D4, F4, E6, and E7. This is known as the Deligne exceptional series of Lie algebras. They obey all sorts of remarkable identities, and I believe these appeared in one of the Gongzhou talks in the F-theory context, or at least some subset of these did. And then there's one more strange thing called E7.5, which I think also appears in F-theory, according to Wadi. It is not a character of a rational conformal field theory, but it is a character of something called an intermediate vertex subalgebra, which has been investigated by Kawasetsu. So given this list, you can then ask yourself, are there relationships between the characters of this theory given by these Hecke operators? And the answer is yes. There's the relationship that I mentioned between affine G2 and the Yang-Lee model. But affine F4 characters are the Hecke images under T13 of the Yang-Lee model. Those of affine E7 are images of affine A1. And even this intermediate vertex subalgebra thing are the images under T19 of the Yang-Lee characters. So when I write these equal signs, we're physicists, but I think this is actually totally rigorous mathematically. You can define these characters as solutions to this modular linear differential equation. Using a recursion relation, you can easily compute the coefficients up to, for thousands of terms. And there's a Sturm bound, which tells you if two modular forms for a certain congruent subgroup are equal up to so many terms, then the two modular forms are equal. And I think for one case here that involved computing something like 30,000 terms, you can do that and show that they're equal. So this is rigorous mathematics, or at least could be turned into rigorous mathematics if these are equal. There's one curious fact which I can't resist mentioning about these two character models with L of W equal to 0, and that is that if you write for the sort of vacuum character that it goes as q to the minus c effective over 24, there's only one of them that's non-unitary, but in order to have a uniform description, it's nice to write it in terms of c effective. And then you define the other character to have leading behavior q to the minus c effective over 24 plus an h effective. Then this is a list of the h effective that appears in that list from Mather, Muki, and Sen. And these numbers are exactly the numbers in the Ferry series F5, except for the first and last elements. I think that must mean something, but I don't know what. It's just a curious observation. So the Ferry series is the ordered set of rational ratios with a maximum denominator 5. Maybe this should be thought of as a kind of trivial theory, and maybe this is affine E8, which is one character. But anyway, this is a curious fact. So they classified the n equals 2 theories where the modular Wronskian has no zeros. But there are solutions where you let the modular Wronskian have zeros. And you can show, so those were investigated in a paper by Nasulich and a more recent paper by Hampa-Perma and Muki. So for example, if L is equal to 2, then if you look back at that formula, the coefficient function is allowed to have a 0 at omega, the orbital point of order 3, and there's a new coefficient function which has to have weight 2 and a 0 at that point, so it has to be E6 over E4, because E4 has a 0 at that point. So you get a new equation, and you can show that the solutions to that new equation, at least those that have positive coefficients that appeared in these other papers, are again Hecke images. And the point here is that taking the Hecke image changes the value of the central charge. It gives you a function that has more singular behavior, so it changes the order at infinity of the modular Wronskian. And eventually, that means from that previous formula involving the order at infinity, that it has to change the number of zeros. And so you can look at various p, and you can look at the number of zeros of the modular Wronskian for the Yang-Lee model. You get a bunch of 0, but then you get 2 and 6, and it goes up and up and up. So you can explain not only the solution relationships between the solutions found by Mathermuki and Sen, you can explain relationships to solutions found in later work where they studied different second-order modular linear differential equations where the coefficient functions had poles corresponding to zeros in the modular Wronskian. So there are many other examples. There's no classification that I know of three-character theories, although there are a number of partial results in the literature. Examples are the Ising model, the tensor product of the Yang-Lee model with itself, another non-unitary minimal model, M72. And there was a recent paper by Hemperper and Muki, which actually was one of the papers that got me interested in this whole business. They explored, but through solutions of a third-order modular differential equation, solutions that had no dimension 1 operators. So without Kac-Moody symmetry, and they found examples that could be characters of rational conformal field theories, that is, only positive or non-negative integers, vacuum appears with degeneracy 1, and the theories they found had central charges 47 over 2, 164 over 5, and 236 over 7. And by comparing their formulas and using recursion, you can show that the solutions they found are, again, all Hecke images of three-character theories. This one is the Hecke image of the Ising model, and it's the baby monster characters. And these other two are Hecke images with respect to T41 and T59. So what else can we do with these? Well, there has been interest in the idea of extremal conformal field theories. I think these first appeared in the PhD thesis of Hone, but then they were famously sort of reinvigorated in a paper by Ed Witten, who proposed them as possible duals of pure gravity in ADS3. I think that conjecture has run into problems, but there are versions of that one could study here. But instead of the theory factorizing holomorphically, it's some finite sum of terms, so it's a rational conformal field theory. But for example, if you start with the Yang-Lee model and you take a prime, or a value of p, which is 7, 13, 47, or 53 mod 60, then the Hecke images satisfy everything that you would like for the characters of a rational conformal field theory. They have non-negative integers, the vacuum appears with degeneracy 1, the fusion coefficients determined from the Verlinde formula are non-negative, but as with Witten's work, there's a problem in that you get too big a gap to be consistent with Virasoro, because there always has to be a Virasoro element 2 up from the vacuum. But you can fix that by adding Hecke images with some coefficients, which have to satisfy an inequality with respect to decomposition of the vacuum character of Virasoro. So you can build these possible characters that are kind of various values of n generalizations of the extremal conformal field theories that Ed was talking about. Good. So, summary. There's a hidden symmetry relating characters of different rational conformal field theories based on Hecke operators. It's a slight generalization of Hecke operators from what exists currently in the mathematical literature, but it's a very minor generalization. It generalizes and extends the previously known Galois symmetry, and the relations appear to be very common. And in addition to the examples that I mentioned with 2 or 3 independent characters, we've been exploring this for more than 3 characters, rational Gaussian models, lattice VOAs, Gepner models, and in every case, we find that there are these Hecke images between many different characters. So it's a very general phenomenon that has been missed because it's a little bit hard to see. So it's natural to wonder whether the Hecke operators have a natural physical origin. Hecke operators appear in the work of Moore, Dijkgraaf, Verlinde on symmetric product orbifolds. And this is a little bit like that, but it doesn't have the orbifold interpretation, and the Hecke operators are not the scalar Hecke operators with these kind of vector value generalizations. On the mathematical side, I explained that the Hecke operators that the Hecke images satisfy modular linear differential equations that have a different divisor structure for the modular Wronskian. It'd be nice to know if there's some nice mathematical theory that explains the divisor of the Hecke images. Perhaps there's some body of knowledge that explains that, but I don't know what it is. So these relations have been gotten by generalizing the Galois symmetry that talks about modular representations, extending that to characters. Does it actually extend to the full rational conformal field theories? Can you actually determine the properties of the Hecke image rational conformal field theory, not just the characters? If that's true, then there are new symmetries acting on the space of rational conformal field theories that have a very strong number theoretic flavor to them. So for Yang-Lee and affine G2, there is some partial evidence in that the braiding and fusing matrices, which we heard about yesterday in Barkeshli's talk, so I won't go through the details of this, but in a modular tensor category that you could extract from rational conformal field theory, there are these braiding and fusing matrices, and the braiding and fusing matrices of the Yang-Lee model and the affine G2 model are related by the same Galois symmetry that relates the representation of the modular group. So, for example, here's the fusion matrix, the non-trivial fusion matrix for Yang-Lee. It's expressed in terms of the golden ratio, G. And under this Frobenius element, G goes to -1/G. And if you do that transformation, you get the non-trivial fusion matrix for affine G2. So rational conformal field theories show up in condensed matter physics in many different places, in the theory of edge states, more recently in the study of entanglement entropy, possibly connected with quantum computation. So this may be a strange thing to say in a string math conference, but I have some fantasy that maybe these Hecke operations might actually be of relevance to the real world through these applications of rational conformal field theory. So thank you very much.